Okay, AP Stats fans, our topic for today, this is lesson 10-2, day 1. This is the sampling distribution for a difference in means. In 10-1, we did the sampling distribution for a difference in proportions. Today, we're going to talk about means. So the nice thing is you're going to see a lot of the same concepts, just some different variables. Before we begin, let me give you your joke of the day. What has more lives than a cat? And the answer is a frog, because it croaks every night. Croaks. All right, so we're going to start. This is the back of a sheet that's on StatsMedic on that website. And just like we did for the proportions, we're going to do a little review from Chapter 7, talking about the sampling distribution of sample means. So we got the sampling distribution of sample means. Now, in Chapter 7, we were only doing this for one mean. But what we learned was when we talk about the shape, we'll talk about shape, center, and spread. Shape, center, and spread. The shape of a sampling distribution of sample means. And remember what this is telling us is if we take every possible sample from a specific sample size and we look at that distribution is what we call the distribution of sample means. That shape will be approximately normal if we know that the sample size is large enough. And when we say large enough, we mean that it's greater than or equal to 30. That is what we call the central limit theorem. If the sample size is large enough, if it's greater than or equal to 30, then we can say that the sample distribution of the sample means is approximately normal. Now, the other time where we can say this is if we know that the population itself is normal. But most times we don't know that, so we use the central limit theorem to approximate normality. Now the center is the mean, but the mean of the sampling distribution of the sample means will be the same. It'll be equal to the actual population mean. The spread, the standard deviation of the sample distribution of sample means, is going to be equal to the standard deviation divided by the square root of the sample size as long as we know that the sample size is less than or equal to 1/10 of the actual population. And that's the 10% rule. And that's assuming that we're choosing people without replacement. If we're replacing them, then that's a different story. Okay, we can use independence there. All right, now, one more thing before we get to the box here. So that was a review from Chapter 7 material, okay? And it's the same thing that we did with proportions. With proportions, we had to do n times p to say that the successes and the failures n times 1 minus p was greater than or equal to 10. The mean of the sample proportions was equal to the actual proportion, the true proportion, and then the standard deviation of the sample proportion was the square root of p times 1 minus p divided by n. Okay, before we get to this box though, we're going to do a second summary. We're going to go back to Chapter 6. And in Chapter 6, we talked about the sum and the difference of two random variables. The sum and the difference of two random variables. The mean of the sum of two random variables is equal to the mean of each individual variable. And the same thing is true for the difference. It would be the mean of x minus the mean of y. The standard deviation of the sum of two random variables Now what we do is we take the square root of the variances. The variance is the standard deviation of standard deviation of x squared plus the standard deviation of y squared. And then for a difference, the standard deviation of the difference is also the standard deviation of x squared plus the standard deviation of y squared. All right, now that's chapter 6 review. This is chapter 7 review. The sampling distribution for a difference in means, well, the shape is approximately normal as long as, if they tell us that the populations, okay, so both populations are normal, that's one way that we can tell that the difference in the means will also, the sampling distribution for the difference in means will also be normal. But since, again, most times we don't know that, the second thing that we can do is the central limit theorem, that n is greater than or equal to 30. And this is for both. We're assuming this is both samples. That's the central limit theorem, CLT. But if we don't have a sample size greater than or equal to 30, we can still use a normal population to approximate if we graph and we see that there are no strong skew or outliers. Okay, so most often we'll be using either the second rule or the third rule here. We'll use the central limit theorem. If we don't have this, we can still take a look at our distribution, and if that doesn't have any strong skew or outliers, we can still use a normal approximation. The center for a sampling distribution for a difference in means, the mean of the difference of the sample means is going to be equal to the mean of the first population minus the mean of the second. Okay, so for a difference of means, we will just take the difference of each population mean. Now remember, the sampling distribution for a sample mean is the same as the population for that. Okay, so this concept we're kind of using here from chapter 6, that when we have a sampling distribution for a difference of means, it's the population mean for the first one minus the population mean for the second. And then the last thing, the spread, the standard deviation. So the standard deviation for the difference of the sample means, of the sampling distribution of the sample means, is the square root, and it's the it's the standard deviation, the first one squared divided by n1, that sample size, plus the standard deviation of the second squared divided by that sample size, which again, so it's the sum of the variances, basically, which is this concept right here. Okay, so what we're doing here is we're taking ideas that we have talked about in previous chapters, and now we're applying them to a new situation. Okay, so this is the sampling distribution for a difference in means. The shape, the center, and there's the spread. Okay, so let's do an example here. Check your understanding, and the question is how tall? The heights of young men follow a normal distribution with the mean for the men is 69.3 inches and the standard deviation for the men is 2.8 inches. The heights of young women follow a normal distribution with mean. The mean of the women is 64.5 inches and the standard deviation is 2.5 inches. Now, it is important that they tell us it follows a normal distribution for the men and it follows a normal distribution for the women. So going ahead, we will be able to assume normality for the differences because they tell us that the actual populations are normal. Suppose we select independent simple random samples of 16 young men and 9 young women and calculate the sample mean heights for the men and for the women. What is the shape of the sampling distribution of the sample mean for the men minus the sample mean of the women? Why? Now, one thing that might be a warning bell to you is that our sample size for the men is 16, the sample size for the women is 9. That does not fit the central limit theorem. That's too small. And we also don't know the individual values for the heights, so we can't graph them to find if there's a strong skew or outliers, but they told us that the populations were normal. The both of them for the men and women were normal. So the shape of the sampling distribution of the sample of men minus the sample mean for the men minus the sample mean for the women, the difference of means, is going to be approximately normal. Because the men and the women's populations are approximately normal. Part B says find the mean of the sampling distributions of the difference in means. Okay, well, we know that the mean of the sample mean for the men minus the sample mean for the women is the same as the true population mean for the men minus the true population mean for the women, which is going to be, now let's see, for the men, the mean is 69.3 inches, and then we're going to subtract. For the women, it is 64.5, and that gives us 4.8 inches. So that is the mean of the sampling distribution of the difference of means. Okay, and then the last piece here is calculate and interpret, we don't want to forget that, the standard deviation of the sampling distribution of the difference of means. Well, the standard deviation of the men's sample mean minus the women's sample mean is going to be the square root of the standard deviation of the men squared divided by the sample size of the men plus the standard deviation of the women squared divided by the sample size of the women. And in this case, we know those values, that the standard deviation for the men was 2.8, and there were 16 of them. So this is going to be 2.8 squared over 16 plus, and then for the women, the standard deviation was 2.5, and that was over 9. So 2.5 squared divided by 9. And now it's a calculator problem. So the square root of 2.8 squared divided by 16 plus, and then it's 2.5 squared divided by 9, and we get 1.088. So 1.088 inches. Now we calculated, but we also need to interpret. And so what this is telling us, the difference in sample means typically varies. This is how we phrase when we're talking about standard deviation. The difference in the sample means typically varies from the true difference in means. Well, typically varies. Let's put the amount. So typically varies 1.088 inches from the true difference in means of 4.8 inches. And that is taking the men minus the women. Okay, so the difference in sample means typically varies 1.088 inches from the true difference in means of 4.8 inches. That's the men minus the women. And that is the end of part 1.